Let's talk about this. This channel is where we explore the most exciting developments in science and technology, especially those with regard to space and time, physics and chemistry, and the origin and evolution of our universe. In one of my previous videos, I tried to explain how it's possible that distant galaxies are receding from us faster than the speed of light, despite the fact that according to Einstein's theory of general relativity, nothing can travel faster than the speed of light. In that video, I showed you how a stretch ruler demonstrates the way space expands, carrying galaxies along with it. However, there's more to the story because that explanation doesn't cover a crucial detail, and that detail is the rate of expansion of the space-time structure itself. Now, before we dive into that, let me ask you a question. Have you ever wondered what's beyond our observable universe? What lies beyond the vast expanse of space that we can see? Well, here's the mind-blowing part. We don't know. Our observable universe is limited by the fact that light hasn't had enough time to reach us from those regions. It's like looking back in time. The farther away an object is, the farther back in time we're seeing it. The universe is expanding, pushing everything away from each other at a rate of 70 kilometers per second per megaparsec of mutual distance. A megaparsec is a unit of length used to measure distances to stars and galaxies, approximately equal to 3.26 million light-years. The rate at which distant galaxies recede from us is proportional to their distance from us. At first glance, you might think that this means distant galaxies are moving faster than the speed of light. But that's not quite right. Let me explain. Imagine you have a balloon with some dots drawn on it. As you inflate the balloon, the dots move apart. The farther apart they are initially, the faster they move away from each other. Now imagine the balloon as the surface of the universe and the dots as galaxies. As the universe expands, galaxies move away from each other. The rate of expansion is currently measured to be about 70 kilometers per second per megaparsec. That means a galaxy that's 1 megaparsec away is receding from us 70 kilometers per second faster than a galaxy that's only half a megaparsec away. And for those of you who prefer miles per hour, that works out to be about 43,430 miles per hour per megaparsec. But here's where things get interesting. The rate of expansion isn't constant, it's actually speeding up. This means that the farther away a galaxy is, the faster it's receding from us, and the faster it will continue to recede into the future. This accelerating expansion was first noticed in the late 1990s, and was one of the key factors that led to the 2011 Nobel Prize in Physics being awarded to 3 scientists. Now here's the thing. You might be wondering why distant galaxies are receding from us at all. And that's due to the fact that our universe is actually expanding. The space between galaxies is increasing, and this stretching of space carries the galaxies along with it. Think of it like a loaf of bread rising in the oven. The dough represents the fabric of space, and the raisins represent the galaxies. As the dough rises, the raisins move apart from each other, and the farther apart they are initially, the faster they move away from each other. However, there's a crucial detail that needs to be considered. The rate at which distant galaxies recede from us depends not just on the rate of expansion of the universe, but also on how far away they are. For example, if 2 galaxies are 10 megaparsecs apart, then the galaxy that's closer to us would appear to be receding at about 700 kilometers per second, whereas the one that's farther away would appear to be receding at about 1,400 kilometers per second. However, if one of these galaxies were to suddenly move closer to us by half the distance between them, say 5 megaparsecs, then the relative speed at which they would appear to be receding from us would decrease to about 1050 kilometers per second for the nearer galaxy and 350 kilometers per second for the farther one. So even though the rate of expansion of space is constant, the relative speed at which distant galaxies recede from us isn't. It depends on how far away they are. So how does this relate to the speed of light? Well, Einstein's theory of general relativity tells us that nothing can travel faster than light. However, that doesn't mean that the space between galaxies can't expand faster than light. The expansion of space is a separate phenomenon from the motion of objects through space. Space itself can stretch faster than light without violating Einstein's theory. For example, consider two galaxies that are so far apart that their light isn't able to reach us. If the space between them expands faster than light, then they will appear to be moving away from each other faster than light, even though they aren't actually moving through space at all. They're just being carried along by the expanding universe. So why do we never observe any galaxy moving away from us faster than light? Well, there's a simple explanation. It's because we never look at individual galaxies when trying to determine the rate of expansion of the universe. Instead, we look at distant galaxies as a whole. By analyzing the light from multiple galaxies, we can measure the rate of expansion of the universe without worrying about the peculiar velocities of the galaxies. And what we find is that while the space between galaxies can expand faster than light, the actual speed of the galaxies relative to us doesn't exceed the speed of light. That's because the peculiar velocities of the galaxies are relatively small compared to the speed of light. They're usually less than 1% of the speed of light. So, when we measure the recession velocity of a galaxy, we're essentially measuring the speed at which the space between us and the galaxy is expanding. To calculate that, we use the following formula: V band h0d, where v is the recession velocity, h0 is the Hubble constant, and d is the distance to the galaxy. The Hubble constant, h0, is a measure of the rate of expansion of the universe. It has a value of 70 kilometers per second per megaparsec. This means that the farther away a galaxy is, the faster it will appear to be receding from us. However, as I mentioned earlier, the rate of expansion of the universe isn't constant. It's actually increasing. This means that the value of h0 isn't constant either. It's increasing over time. This acceleration of the expansion rate was first noticed in the late 1990s and was one of the key factors that led to the 2011 Nobel Prize in Physics being awarded to 3 scientists. But what does this mean for the speed of light? Does it mean that there's a region of the universe where the speed of light is exceeded? Well, no. Remember that the speed of light is a fundamental constant of nature. It doesn't change. The fact that the rate of expansion of the universe is increasing doesn't change the fact that the speed of light is the ultimate speed limit. The reason why distant galaxies can appear to be receding from us faster than light is because the space between us and those galaxies is expanding faster than light. But that doesn't mean that the galaxies themselves are traveling faster than light. So what's beyond the present mutual distance between objects in the universe of about 46 billion light years, which is the detectable part of the universe? Well, to answer that question, we need to take into account the fact that the rate of expansion of the universe is increasing. This means that the distance between objects is increasing at an accelerating rate. If we were to extrapolate this trend, we would find that at some point the distance between objects would increase faster than the speed of light. However, this doesn't mean that anything is traveling faster than light. It just means that the space between objects is expanding faster than light. In other words, there's a region of the universe that's so far away from us that its light hasn't had time to reach us yet. And since we can't see beyond the detectable part of the universe, we don't know what's out there. It could be anything. It could be more galaxies, more stars, or even other universes. But here's the thing. Just because we can't detect anything beyond the observable universe doesn't mean that it doesn't exist. It's just that the space between us and those regions is expanding faster than the speed of light. This may seem like a strange concept to grasp, but it's actually quite simple. The space between us and distant galaxies is expanding at an accelerating rate. This means that at some point, the distance between objects will increase faster than the speed of light. However, this doesn't mean that anything is traveling faster than light. It just means that the space between objects is expanding faster than light. In other words, there's a region of the universe that is so far away from us that its light hasn't had time to reach us yet. And since we can't see beyond the detectable part of the universe, we don't know what's out there. It could be anything. It could be more galaxies, more stars, or even other universes. But here's the thing. Just because we can't detect anything beyond the observable universe doesn't mean that it doesn't exist. It's just that the space between us and those regions is expanding faster than the speed of light. So what does this all mean? Well, it means that the universe is a pretty big place and we've only explored a tiny part of it. There's so much out there that we don't know about, and it's expanding at an accelerating rate. Who knows what we might find if we could just figure out a way to travel faster than light. Thanks for watching. Let me know what you think in the comments below. And as always, thanks for watching. I hope you learned something new, and if you did, please leave a like and subscribe. Your support helps me to continue making great videos. Thanks again, and see you next time.